In the study of calculus, there are three basic theorems about continuous functions, and one is intermediate value theorem, second one is maximum value theorem, and the third one is uniform continuity theorem. The maximum value theorem is used for proving mean value theorem for derivatives upon which the fundamental theorem of calculus depend. The uniform continuity theorem is used among other things for proving that every continuous function is integrable. We have spoken of these theorems as a theorem about continuous function, but it can be considered as a theorem about closed interval AB of real numbers. It depends not only on continuity of F but also property of topological space AB. The property of space on which maximum value theorem and uniform continuity theorem depend is called compactness, and it is a fundamental notion in higher analysis, geometry, and topology. Indeed, in almost any subject for which the notion of topological space itself is relevant. Suppose we are given an arbitrary space X. There is a natural way to break it up into pieces that are connected or path connected. So, first of all, we will start with defining the component. Suppose we define an equivalence relation on X by setting X equivalent to Y if there is a connected space C of X containing both X and Y, means X and Y are elements of C. The equivalence classes are called the components or the corrected components of X. This relation, which is defined like there is a connected space C of X containing both X and Y, is an equivalence relation on X. To prove that it is an equivalence relation, we need three things: symmetry, reflexivity, and transitivity. Here, symmetry and reflexivity of the relation are obvious. And for the third one, if A is connected subspace of X containing X and Y, and if B is connected subspace containing Y and Z, then A union B is a subspace containing X and Z that is connected because A and B have the point Y in common. Hence, it means this relation is also transitivity. It means this is a equivalence relation. Now we will prove one theorem which states that the components of X are connected disjoint subspaces of X whose union is X, such that each non-empty connected subspace of X intersects only one of them, or we say that is contained in precisely one component. We know that being an equivalence class, the component of X are disjoint and their union is X. Each connected subspace A of X intersects only one of them. Because if A intersect two components C1 and C2 of X, say in points x1 and x2 respectively, then x1 is equivalent to x2 by definition. And this is not possible unless C1 is equal to C2. Now we need to show that each component of C is connected. So to prove this, suppose we select a point x0 belonging to C. For each point x belonging to C, we know that this x0 is equivalent to x. So there is a connected subspace AX containing both x0 and x. It means AX is a subset of C. Or we can write C is equal to union of AX where x belongs to C. Since the subspaces of AX are connected and have the point x0 in common, their union is also connected. Hence, the theorem follows. Now we define a path. Suppose x and y are given points of topological space X. A path in X from a point X to another point Y is a continuous map F from closed interval AB to X of some closed interval in the real line into x so that fa is equal to x and fp equal to y. Now, path connectedness. A space X is said to be path connected if every pair of points xy belonging to X can be joined by a path in X. It is easy to see that path connected space X is also connected. Suppose X is equal to A union B is a separation of X, and let F from AB to X is any path in X. Being the continuous image of connected set, the set FAB, FAB is the image of closed interval AB under F is connected. So it lies entirely in either A or in B. Therefore, there is no path in X joining a point of A to a point of B, which is a contradiction to the assumption that X is a path connected. The converse of this statement need not be true. Means connected space need not be path connected, although path connected space X is connected. Now we will define path component like components. We define one more equivalence relation on topological space X by defining X equivalent to Y if there is a path in X from X to Y, and the equivalence classes are called path components of X. Now we will prove one more lemma that this equivalence class, this relation is an equivalence relation on X. So to prove that this is an equivalence relation on X, first of all we notice that if there exists a path F from closed interval AB to X, from X to Y whose domain is in the interval AB, and there is also a path G from X to Y having a closed interval AB as its domain, because two closed intervals in the set of real numbers are homeomorphic. Now, since X is equivalent to X for each X in X, because there exists a constant path F from closed interval AB to X defined by Ft equal to X for all t. It means X is equivalent to X, or it means this relation is symmetric. Oh, sorry, reflexive. Now to prove the symmetry, suppose F is a path from closed interval AB to 0, 1 to X. Then the reverse path G from 0, 1 to X is defined as Gt equal to F of 1 minus T. And it is a path from Y to X. This is a path from X to Y. And this is a path from Y to X. It means the relation is symmetric because we can find the reverse path also. Finally, we prove the transitivity of the relation. Suppose F is a path from X to Y and G is a path from Y to Z. Now we can paste F and G together to get a path H from 0 to 2, X from X to Z. The path H will be continuous by the pasting lemma. What is pasting lemma? Suppose X is equal to A union B, where A and B are closed in X. Suppose F is a mapping from A to Y and G is a mapping from B to Y. And suppose F and G are continuous. If Fx is equal to Gx for all x belonging to A intersection B, then F and G combine to give a continuous function h from x to y defined by setting hx equal to fx if x belongs to A and hx equal to gx if x belongs to B. So using this pasting lemma, we prove that this relation is also transitive. So we have shown reflexivity, symmetry, and transitivity. It means this relation is an equivalence relation on X. Now we have one more theorem. In fact, similar theorem. The path component of X are path connected disjoint subspaces of X whose union is X such that each non-empty path connected subspace of X intersects only one of them. Means it is contained in precisely one path component. The proof of this theorem is similar to that of the preceding theorem. We notice that each component of a space X is closed in X since the closure of connected subspace of X is connected. If X has infinitely many components, then each component is also open in X since its component is finite union of closed sets. But in general, the component of X need not be open in X. Path component of X is neither open nor closed in X. Now we have some example. Suppose Q is a set of rational number and R is a set of real number. If Q is a subspace of R, then each component of Q consists of single point and none of the component of Q are open in Q. One more example, the topology sine curve S bar equal to S union V is a space that has single component because it is connected and two path components S and V. One path component is the curve S and other is the vertical interval V equal to 0 cross minus 1 to 1. We notice that S is open in S bar means topology is sine curve but not closed, while V is closed in S bar but not open. If one forms a space from S bar by deleting all the points of V having rational second coordinate, one contains a space that has only one component but uncountably many path components. Now we will define local connectedness. A space X is said to be locally connected at X if for every neighborhood U of X there is a connected neighborhood V of X contained in U. Means X belongs to V which is a subset of U and which is a subset of X. Roughly speaking, local connectedness means that each point has arbitrarily small neighborhood that are connected. If X is locally connected at each of its points, then it is said to be locally connected. Now, locally path connected. A space X is said to be locally path connected at X, where X is a point of capital X. If for every neighborhood U of X, there is a path connected neighborhood V of X contained in U. Means X belongs to V, which is a subset of U, which is a subset of X. If X is locally connected at each of its point, then it is said to be locally path connected. We have some examples. Each interval and each ray in real line is both connected and locally connected. The real line is locally or path connected since each neighborhood U of any point X contains a path connected basis neighborhood X minus epsilon to X plus epsilon for some epsilon greater than 0. Any open subset omega of Rn is locally path connected since each neighborhood U of any point X belonging to omega contains a path connected basis neighborhood open ball BD centered at X and radius epsilon for some epsilon greater than 0. The subspace minus 1 to 0, union 0 to 1, it is closed at minus 1, it is closed at 1 and it is open at 0. So this subspace of R is not connected, but it is locally connected. The topology sine curve is connected but not locally connected since small uh, neighborhoods of points in V are not connected. The set of rationals Q are neither connected nor locally connected. Now we have one theorem. A space X is locally connected if and only if for every open set U of X, each component of U is open in X. Suppose X is locally connected. Now we will prove that for every open set U of X, each component of U is open in X. Suppose U be open set in X and let C be component of U. Now we will prove that the C is open in X. If X is a point of C, we can choose a connected neighborhood V of X such that V is a subset of U. Since V is connected, it must lie entirely in the component C of U. Hence, C contains a neighborhood around each of its points. Therefore, C is open in X. Now, for the converse part, suppose that components of open sets in X are open. Now, we will prove that space is locally connected. Suppose we are given a point X of topological space X and a neighborhood U of X. Let C be the component of U containing X. Now, since C is connected, since it is open in X by hypothesis, X is locally connected at X. A similar proof holds for the following theorem. A space X is locally path connected if and only if every open set U of X, each path component of U is open in X. The relation between path component and component is given by this theorem. If X is a topological space, each path component of X lies in component of X. If X is locally path connected, then the components and the path components of X are same. Suppose C is a component of X and X belongs to C. Let P be the path component of X containing X. Since P is connected, therefore P is a subset of C, each path component P is non-empty and connected, hence lies in a unique component C. Now we want to show that X is locally path connected, means then P equal to C. Suppose P is not a subset of C. Let Q denote the union of all the path components of X that are different from P and intersects C. Each of them necessarily lies in C, so that C is equal to P union Q. Because X is locally path connected, each path component of X is open in X. Therefore, P, which is a path component, and Q, which is a union of path components, are open in X. So they form a separation of C. This contradicts the fact that C is connected. Thank you.